All right, welcome to lesson 1.2. We're going to cover force vectors and equilibrium of a particle in two dimensions. By the end of this lesson, you're going to understand what a vector is and how it is different from a scalar, perform basic vector operations such as vector addition and resolve a vector into components. You're going to define a particle with special regard to statics, draw free body diagrams of particles. Can't emphasize that one enough, and utilize the equations of equilibrium to determine the internal axial forces inside 2D particle problems. A little bit of terminology that you should already know, but just to jar your memory, a scalar is a physical quantity that has magnitude, while a vector has magnitude and direction. The old example of speed being a scalar, velocity being a vector. Right? Speed is just you're driving 65 miles per hour when you got pulled over. The vector was you were driving 65 miles per hour to the emergency room that was 33 degrees northwest of your location when you got pulled over. Some examples. Mass is a scalar, force is a vector. That's a good one to talk about in statics, right? Mass, kilograms, force, newtons. We're going to be dealing with vectors here, so force in newtons versus kilograms in mass. So remember, a rigid body is something we're going to be looking at, but first, let's talk about the specific case of a particle. That's what we're going to concentrate on this lesson. Particle is a rigid body. It has mass, perhaps, but the size can be neglected. It's a tiny little dot. Okay? All of our forces in these rigid particles problems are going to be concurrent. They're all going to pass through the dot. That's going to be important. A force, an action of one body or particle on another body or particle. Force is a vector. Okay. Speaking of vectors, what can you do to multiply or divide a vector by a scalar? Well, if it is a scalar, like if you're just multiplying a force by 2, the scalar 2, you make the vector twice as long as it was before. So F becomes 2F when you multiply it by 2. If you multiply it by -1, it becomes -F. And look at that, the direction flips. Negative just means the vector is pointing 180 degrees from the positive. And then obviously you can multiply by -0.52, yada, yada, yada. Vector addition using the parallelogram law. So remember, vectors are not scalars. You cannot just add their numbers together. You can't just do, if F1 is 90 pounds and F2 is 90 pounds, you don't get 180 pounds because these two vectors are not pointing in the same direction, as you can clearly see. So what you have to do is take the vectors and make a parallelogram, okay? And this parallelogram, this red line here is parallel to that line there. This blue line parallel to that line there. And then starting at the tail of these two vectors, draw a vector to the end of these two, and that is your resultant. Okay, and that would be, we're naming it FR here, F sub R for resultant. It's the summation of F1 and F2. Okay, that was the parallelogram law, which showed you how to build a parallelogram and analyze it to see where the resultant is. This is basically the same thing, but instead of thinking about it as the parallelogram with a slice through the middle of it that is your resultant, the triangle rule just looks at half of that parallelogram. And the way we're going to do this, we're going to put the tail of one of our vectors, we're going to move it just for graphical purposes. You're not really allowed to move vectors side to side without having impacts. You can move them along their line of action, of course. Remember, your line of action of a vector, that should be in my terminology too, but I don't have it in there. The line of action is that infinite line that points along the line of that force. You can move along that length from a mathematical point of view, and you don't really have any serious impact, but you can't slide them off of that line. So this is really just a graphical thing we're going to do. We're going to put the tail of one vector at the head of the last vector, and then you're going to draw your resultant, which will start at the tail of your first vector and end at the head of your last vector. So if we do f1 plus f2, we move f2 and stick on the end of f1. See the tail of f2 stuck onto the end of f1. And then our resultant will start at the tail of our first vector and end at the head of our last vector. And we have f1 plus f2 equals r. Or we could have done f2 plus f1 and get the same thing. If you took these two triangles and squashed them together, you'd have that parallelogram we looked at on the previous slide. Okay, so that's how you can add these vectors together. How do you subtract a vector? f1 minus f2. Why don't you just add its negative? Like we said earlier, if you put a negative in front of it, you're flipping its directions. So that just means we need to flip the direction of one of the vectors. So if we're doing f1 minus f2, we're going to draw f2 backwards, right? Because it is now the negative, and then the resultant is that. So we're just adding the negative. All right? Cool. How can you add more than two concurrent vectors graphically? Well, you could draw this whole line of things, of all these vectors stacked tail to head, tail to head, tail to head, tail to head, and your resultant would be starting at the tail of the very first vector and ending at the head of the very last vector. And that still works, but the problem is that you don't have the geometry tools there to solve for its value. Triangles are great, right? Because you can start to find the lengths of sides either using basic right angle triangle trigonometry, or by using law of cosines and law of sines and stuff like that. Okay, so if you want to add them, actually get numbers, really what you have to do is you have to add, if you have three vectors, f1, f2, and f3, you might add f1 and f2 together, get an intermediate resultant, and then add f3 to that resultant. So you're going to do this whole thing twice. And it doesn't matter what order you do it in. You could have added f1 and f3 and gotten a result, and then added that to f2. It will all get you to the same place, but it's a multi-step process, which is kind of a bummer if you ask me. That is a problem with the graphical system of adding vectors. It's great for two vectors. If you have more than two, it starts to really slow down. All right, the law of cosines and the law of sines. This is how these are the tools you use to solve for the resultant value if you have a vector addition problem like this. If you have f1 and f2, these are the vectors we had earlier, right? There's going to be an angle between them, which is this angle C. And that angle might seem obvious on this page. It's usually not terribly obvious in the problem, because didn't you move f2 up there? You might know where f2 is in relation to the horizontal. You might know where f1 is in relation to the horizontal. So you have to kind of figure out that angle C. And that's, kind of a bummer. But it's not the end of the world. I have some examples that show that. But once you know that, then you have f1's value, you have f2's value, their magnitudes. And now that you know that angle value C, you can build by the law of cosines this and find the resultant force magnitude as the square root of f1 squared plus f2 squared minus 2 times f1 f2 cosine C. That is the law of cosines written in terms of this triangle with its labels. All right, the law of sines is also a cool geometric thing that we can do. And it's maybe it's a little easier to see. It's kind of got its problems, though. Here we can say that that any side can be divided by the sine of the angle opposite it, and that would be equal to any other side divided by by the sine of the angle opposite of it. So here I say f sub r over sine of C is equal to f sub 1 over sine of A. So f sub r over sine of C is equal to f sub 1 over sine of A. That also happens to be equal to f sub 2 over the sine of B. Problems with that? Well, this is great and all once you have one of the angles like C, and you have the magnitude f sub r, which usually we don't have that. So normally you have to run the law of cosines first, and then maybe you can use the law of sines, granted, okay? There is a small issue with the law of sines. Sometimes it pops up. It pops up in the example we'll go over in a few seconds here. Remember that the sine of you want to solve for one of these angles, right? So because say we solve for f sub r here, right? We know c because we figured it out. We know 1 because it was given. Law of sines gave us f sub r. So if we look at like these two right here, we would have that value, this value, and this value. We could solve for that value. Well, to do it, we do arc sine. And then once you do arc sine, remember it's always going to give you that smallest value of the angle. If it's less than 90 degrees, well, it's going to give you a value usually less than 90 degrees if you plug that into your calculator, right? Keep in mind that the angle A might not, as it's drawn here, of course, but these angles over here, they might be greater than 90 degrees sometimes. You know, C doesn't have to be the largest angle. You'll see it here in a second. So the way you can work around that is there's two ways. One is you could actually, instead of using the law of sines, use the law of cosines, but instead of f sub r, have it one of the other sides, right? If you wanted to find this angle B, you could use f sub 2 over here, and then you would have f sub r squared plus f sub 1 squared minus 2 times f sub r times f sub 1 times the cosine of B. This works, remember the law of cosines works for any of the sides. It doesn't just, this side over here doesn't have to be the hypotenuse. And then you would solve for the angle. That's one way to do it, and that'll give you a more exact number. You won't have that ambiguous case where it's either maybe the angle is less than 90, but maybe it was greater than 90 type of thing. It's a better answer for that. It takes a little bit longer. The other way you can check it is to, if you are solving for A, you could use maybe these two expressions, do that, find that angle, then run this one as well, find B, and then add the angles A, B, and C together. They need to equal 180 degrees, right, if they're a triangle. So if they don't equal 180 degrees, if they're less than 180 degrees, one of these angles is not right, and it's probably because of this ambiguous case. So then subtract that angle value from 180, and you'll get the angle that it is. Because the sine of 60, for instance, is the same as the sine of, 120, right, 120 degrees. All right, anyway, we'll see that in this example.